Hi everyone, I'm honored to present the paper TriangleNet towards Robustness in point cloud learning. Point cloud-based object classification is becoming the default approach for 3D sensing. For example, autonomous vehicles rely on point cloud sampled by deep cameras for the effective navigation. Service robots and bell robotics may use tactile to interact with the environment, of which the contact information is also being processed in the point cloud format. However, challenges often faced in point cloud processing include sparsity, rotation, noise, and occlusion. For autonomous driving, the point density decreases when the distance to the deep sensor increases. In tactile exploration, the object point cloud is not only sparse due to the low sensing resolution, but also subject to the unknown object pose. This implies that the sparsity and other types of disturbances may be combined in real applications. Unfortunately, we found that a majority of 3D classifiers are not robust to such multifactorial disturbances. As an example, we show that PointNet is not able to resist the combined variations from the sparsity and the rotation. Using ModelNet 40 dataset, we trained and tested the PointNet under 3 rotation conditions in 4 different point cloud densities, as indicated in the row and column. We used the accuracy drop as a metric to evaluate the robustness. The result shows that PointNet has good resiliency towards the sparsity or the rotation, but only when it appears alone, as implied in the green and blue annotations. However, the accuracy drops significantly when the sparsity and the rotation are combined, as implied in the red annotations. We introduce our method as follows. Similar to the PFH descriptor that are widely used, a feature can be constructed by 2 points and the surface normals. The distances and the angles are collected as the feature vector. However, only using 2 points will result in limited discriminability. Therefore, we expand this concept to a combination of 3 points, in which the spatial relationship between points are enhanced. We call it a triangle feature. Furthermore, we found that adding more triangular parameters related to the gravity center can further enhance the performance in our learning algorithm that will be introduced later. The feature we use in practice is the DC function shown in this equation. Next, we propose TriangleNet, a deep learning structure that facilitates machine learning to be conducted on sparse and rotated point clouds. We map the triangle feature to its latent representation by a multi-layer perception network. To get the point-wise feature for segmentation task, we aggregate the triangle features that share the same vertex point xi by a max operation. Then we calculate the global feature by aggregating from all point-wise features. The global feature is used as a classification and object reconstruction. We evaluate our approach under 2 scenarios. First, global sparsity, meaning the point is only characterized by sparse points. And second, partial sparsity, meaning a part of the points is sparser than the rest parts. We use ModelNet 40 to evaluate the global sparsity setting, and scan object NN dataset for the partial sparsity setting. Here, we showcase the quantitative results. The advantage is significant in both datasets as the rotated point clouds become exceedingly sparse. The discriminative power of our method can also be visualized by the TSNE analysis. The visualized distributions showcase that our latent representations are distinctive even for extremely sparse point clouds. In practice, sensor measurements include outlier points and inaccurate surface normals. To answer whether our approach can be robust to such noisy inputs, we conducted noise injection experiments. Qualitative results are shown in the figure A and B. Our algorithm can also achieve the scale invariance by normalizing the side length of the triangle features. The result is shown in the figure C. The blue curve corresponds to the result using the scale normalization trick. We qualitatively show the results of voxel reconstruction and the point segmentation using only 16 points per object with arbitrary rotation. We summarize our key contributions as follows. First, we demonstrate by experiment that the majority of 3D machine learning algorithms cannot learn robustly on multifactorial disturbances. As a solution, we propose a feature that is robust to versatile variations, based on which we design our TriangleNet, a deep learning model that allows many applications to be built on extremely sparse points with multifactorial variations. Thank you for your attention.